right, ladies and gentlemen, it is
I got something right, but like the main stuff.
11/21.
We still want
21st of November. Our what?
I think it's because we were like really cool.
No,
I said first, not one.
not yeah. I mean, it'll be before finals. December, like 18th and 19th. So, not in December, but in May, something there. Okay, good afternoon. Here we go. We are graphing log functions today. And to graph log functions, I think that I teach a very easy way to graph log functions by hand. Many of you maybe already know how to use your calculator. It has some fancy modes that you can figure out, but to graph them by hand is actually pretty easy. And it utilizes these two rules. So log base b of 1 equals what? 0. Why? Because anything to a power of 0 equals 1. Because if you give it a swirly, it makes total sense. Okay? So log base b of b is equal to 1. Why? Because anything to the first is itself. Yes, again, because if you give it a swirly, it makes perfect sense. So, ladies and gentlemen, when you have log equations, really take the time to really think through why does this make sense. And if you always go back to the swirly, then it really does make a whole lot of sense. So we're graphing log functions today, and we're going to utilize this rule. Log base b of x equals y. And this is going to help us figure out some ordered pairs that we can graph really easily. So just like we were graphing exponential functions, we had a base graph that was really easy to find with a little XY chart, and then we were shifted. We'll do the same thing here. Okay. So example 1. Graph the log function, identify the domain range and vertical asymptote. So just like the exponential function, we're going to graph a really simple base graph and then shift it h and k units. Now logs and exponentials are inverses of one another, so everything is the opposite, essentially. And exponential functions, that's our Superman graph. So our Superman exponential function had a horizontal asymptote. So our log functions have a vertical asymptote. They're the opposite. Okay, so instead of a horizontal line, we have a vertical line as the asymptote. So I'm going to start. I guess I could write down the generic function for you. Y equals a times log base b of x minus h plus k. So this is sort of the generic form of our log function. And we will graph just this really simple base function right here. Makes it really easy to figure out. And then the h is going to shift our graph left and right, and the k shifts it up and down. So pretty easy. All right, so we have here y equals log base 3 of x. This is going to be our base graph. And I'm going to make a real simple xy chart. Log base 3 of x equals our y value to figure out some ordered pairs that we can graph. And we're going to utilize those rules we just talked about. One of the rules was log of 1. By plugging a 1 for x, log base 3 of 1 equals what?
0.
0. Why? Because 3 to the 0 equals 1. Again, if you give it a swirly, that makes perfect sense. Okay. What's another good number we could plug in for x? 3. Sure. Because log base 3 of 3 equals 1. Again, why? Because 3 to the first equals 3. Again, if you give it a swirly, that statement makes perfect sense. Okay. There are lots of other numbers that we could choose as well. Like 9 is a good choice. Log base 3 of 9 equals 2. Okay, because 3 squared is 9. And we could also choose like 1/3. Log base 3 of 1/3 equals -1. 3 to the -1 power gives you 1/3. So there's lots of good numbers that you can choose, but really we only need 2 of them. The only reason I did some extras is so we can see a little bit better the shape of this graph. So first I have this point 0, 1. Then I have the point 3, 1. I also have the point 1/3 on the x-axis, -1. That's like right here. And I have the point 9, 2. 9 is way out here, and it only goes up to. This function, this base graph, all of these base graphs, have a vertical asymptote that begins at x equals 0. And this is the basic shape of the log graph. I lovingly call this graph the log ride. Just like exponential is the Superman graph, this is the log ride. And I really hate log rides because on a log ride, you sit on the log, right? And on every single log ride, every single one, the first thing you do is go up. Click, 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 right? Right? Every single time. So that's what's happening here. Up. Click, 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 click. And then it's like it's a freaking small world. And you just float around and it doesn't do anything.
And then
right?
you go down.
And then you go down at the very end.
Actually, you go up again.
But really, so I mean, Pirates of the Caribbean is the only ride on water that is really, really cool. But okay. So this is my log ride. It sort of just goes up, 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 and then just sort of fizzles out. It doesn't do much. Okay. Logarithmic graphs grow really, 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 really slowly. But it is an increasing function. It's just slow. It gets really, really slow. Now we graph the base function and we need to shift it. How is our graph going to be shifted? Left 2 units and down 4. All right. So I'm going to shift. I just need 2 points. These first 2 points are really the best ones to use. I'm just going to shift them left 2, 1, 2, and down 1, 2, 3, 4. And go left 2, down 1, 2, 3, 4. And so if I'm shifting my graph, what happens to my asymptote that was here at x equals 0? It shifted left 2. Does it shift down 4? Does it matter? No. Yeah. It's a line. It goes on forever. So that vertical asymptote gets shifted. So it turns out that this inside piece here, whatever is with x, that is going to determine your vertical asymptote. X equals h. So if you solve that equation, x minus h equals 0, that's going to give you your vertical asymptote. Always, always. Now looking at the blue graph, what is the domain? How far left does it go? -2. -2. And how far right does it go? Infinity. How low and how high does it go? All real numbers. Yeah, forever down and forever up. I'm just going to put a big fat R there for all the real numbers. And then the vertical asymptote is x equals -2. And again, that comes from whatever is with x on the inside of the function. Okay. All right. This is a base greater than 1. This is a base value less than 1. This 3, is it on the inside or the outside of the function? Outside. This is the k value. There's no parentheses here, so there's no horizontal shift on this one. So this is our base function, And again, I'm just going to do a real simple XY chart for log base 1/4 of X, and that's going to equal our Y value. What are some good numbers to plug in for X? 1 and 1/4. The numbers we're going to plug in for X are always 1 and the base. Always, always. Because the log of 1 is always equal to what? 0. The log of 1 always equals 0. No matter what the base is, the log of 1 is 0. And again, if you give it a swirly, 1/4 to a power of 0 equals 1. So that makes perfect sense. And then log base 1/4 of 1/4 always equals 1. Again, if you give it a swirly, 1/4 to the first power is 1/4. So these are two great values. We have the 0.10 and we have the 1/4, 1. 1/4, oh, that's up. What do you think is going on with this function? Oh.
It's going down.
It's a decreasing function. So the base is less than 1. And so this is now a decreasing logarithmic function. All right, so if the base is between 0 and 1, then it's a decreasing, a downhill log graph. All right, it does have that vertical asymptote right here at x equals 0. And then how are we going to shift this function? Down 3. This is the outside value. It goes down 3 units. There's no horizontal shift on this one. So we're going to go down 1, down 2, down 3. Down 1, down 2, down 3. Does my vertical asymptote change?
Nah.
Nope. So there's my blue graph. What's the domain? 0 to infinity. You'll notice I'm using parentheses there. Why parentheses and not brackets?
It doesn't exist.
It can't equal because we have an asymptote, right? Good. The range is all real numbers, and our vertical asymptote is at x equals 0 for this one. So watch that shape of those graphs. Any questions on graphing? Oh, we're done. Last thing. Example 2, use the one-to-one property to solve the log equations. So the one-to-one property is super useful. Really, it's just looking at what things are equal. So if we know that some things are equal, then other parts must also be equal in order for the two sides to be equal. So here we have log, what are the bases there? 10, very good. Whenever you don't see the base, it is base 10. And that is because it's called the common logarithm. And we use base 10 because our number system is base 10. Okay, 10 digits, 10 toes, 10 fingers, usually. Okay. All right. So these logs are equal. So what must we know? The 5x minus 7 equals 3x. Yeah. If the logs match, then the other stuff must match as well. Just like our one-to-one property when we were doing exponents. If the bases match, then the exponents must match. Here, if our logs match, then our arguments must match. Same exact thing. So I have, let's see, negative 2x is equal to negative 7, which means x equals 7 over 2. 7 over 2.
Bless you.
Thank you. All right. Letter B. A little bit harder. Log base 5 of 7 minus 3x squared equals log base 5 of negative 2x squared minus 6x. Oh, I think I blew out my neck on that.
That might be the first time you sneezed in here.
All right. So again, since the logs match, what do we know? The arguments must equal each other. So 7 minus 3x squared must equal negative 2x squared minus 6x. And how do you solve something like that? Combine like terms. Set them all equal to 0. Yeah, I'm gonna slide these all over to the right side. That's gonna give me a positive 3x squared, and a negative 2x squared is a 1x squared, a negative 6x, and a negative 7. And then what do we do? Factor. X times x is x squared. What times what is negative 7? Negative 7 and positive 1. And so we get solutions for x. X equals 7 and x equals negative 1. Now here's where it's really tricky. Logarithms have a vertical asymptote. So if you're thinking about the log base 5 of x, whatever the base happens to be, that graph has a vertical asymptote at x. And the graph is everything to the right, which means whatever is in here, which is in the argument, must be greater than 0. So what I have to do is I need to check some answers. So I'm going to plug in my 7 and see what happens. Log base 5 of 7 minus 3 times 7 squared is supposed to equal log base 5 of negative 2 times 7 squared minus 6 times 7. Okay, so what happens here? I get math I can't do in my head.
Can we just graph these?
Can you graph log base 5?
Yeah. We don't know that.
Oh, the divide thing. Yeah, I haven't taught you that yet. Okay, that was totally not right. 7 minus 3 times 7 squared. Okay. All right. So what I have here is log base 5. My argument is negative 140. 7 minus 3 times 49 is negative 140. Negative 140 is way over here. Is there any picture way over here in negative 140 land? No, it's undefined. Negative 140 land, yes.
But what if it
The argument must be greater than 0. X has to be greater than 0. That's what the domain is. The argument, we cannot take the log of a negative number. This does not work, which means 7 is a false solution. Okay, now negative 1, when you plug negative 1 in, we would have 7 minus 3 times negative 1 squared. Well, that would be 7 minus 3, which is 4. Log base 5 of 4 is totally okay. 4 is a positive value. That's allowed, okay? But we cannot take the log of a negative argument. You'll notice I'm saying argument. The stuff inside the logarithm has to be positive. Okay, so negative 1 is a solution that's going to work. All right, do you have any questions for me?
Yeah.
All right. Pass out the worksheet.